Ever notice how, like, some numbers just feel right when you divide them up? Like 12, 6 pairs, 4 groups of 3, you know?
Yeah.
Turns out there's a whole area of math for this. Who knew? We're going deep today, diving into these things called divisors. Got our trusty OEIS, the online encyclopedia of integer sequences for the cool kids, and their entry on sequence US, 000005, the divisor function.
Okay.
Oh, in a Wikipedia article on, you guessed it, divisor function.
That sounds.
By the end of this, you'll be fluent in divisor speak, understand their quirks and why mathematicians are so into them.
I'm intrigued already.
It's way more interesting than it sounds, trust me.
What gets me is how something simple, like what divides into this number, can blow up into these huge math concepts, like a thread through a giant tapestry.
Okay, so divisor function sounds like a textbook threw up, right?
That did, yeah.
But it just means how many numbers divide evenly into this one.
Oh, okay.
We write it DAN, or sometimes that sigma thing, ZON, mathematicians and their Greek letters. Right.
So D12 is 6, because 12 has 6 divisors. 1, 2, 3, 4, 6, and 12 itself.
Like a number's divisibility factor, then. Higher the divisor function, the more ways you can split it up.
Back to that cake slicing thing.
Yeah.
This is real-world stuff, believe it or not, like arranging objects into a perfect rectangle.
Really?
Yeah. The OEIS mentions how many ways to do that's directly tied to the number's divisors. Rows and columns, those grids we see everywhere.
Huh, okay. And this is where prime numbers come in, those like VIPs of numbers.
Prime numbers, always the stars. What makes them so special in divisor world?
Well, primes are like the atoms of multiplication.
Okay.
Everything else is built from them. A prime number. Only 2 divisors, 1 and itself. So D2 is just 2. But it gets interesting with prime powers. Take 2 cubed, that's 8. Divisors are 1, 2, 4, and 8. That's 4 divisors. See it?
Wait, it's just the exponent plus 1, so D23 equals 4, because 3 plus 1 equals 4.
Exactly.
That's surprisingly neat. And it works for any prime number, however high you raise it. Shows how fundamental primes are to building all other numbers.
Okay, my mind is slightly blown. So we've got these building blocks, the primes, and now we want to see how they make divisors for bigger, more complex numbers. That's the multiplicative function part, right?
Right. And less scary than it sounds.
Yeah.
Imagine outfits. You've got, say, 3 shirts, 4 pairs of pants.
Okay, I like where this is going.
You've got 12 outfits possible, because 3 times 4 is 12. Divisor function similar.
So if we know the divisors of 2 numbers, and they don't share factors, we just multiply their divisors to get the divisors of their product.
Exactly. Picture it. The number 12, it's 2 times 2 times 3, or 2 squared times 3.
Right, right.
Now, 2 squared is 4, has 3 divisors. 3 has 2 divisors. Multiply those, you get 6 divisors for 12, just like we saw. It all comes back to that prime factorization. Those prime building blocks are always there, shaping the number's properties.
Okay, I'm seeing how these prime numbers are like the puppet masters of divisors. But you know what's cool?
What's that?
The OEIS mentions this thing about divisors and partitions.
Oh, yeah.
Tell me more. I'm kind of interested.
Partitions are like those rectangles we talked about, but with, like, another dimension. Imagine splitting candy amongst friends.
Okay.
Partitions are all the ways to divide the candy, each friend getting a whole number.
So if I've got 12 candies, I could do 4 to 3 friends, or 6 to 2 friends, or, oh, okay, I get it.
Exactly. And each of those is like a divisor of 12. It's about finding those same size groups inside a number. Divisors aren't just how many, but the relationships they make inside a number.
Mind blown. It's like divisors are the cheat code to how numbers break up and reform.
And speaking of codes, ready for a real math mystery.
Ooh, I love a good mystery, especially with numbers. Hit me.
All right, so remember how primes have those big unsolved problems? There's this thing called Robbins' theorem. It's a math hunch, connecting the divisor function to one of the biggest unsolved things ever, the Riemann hypothesis.
Hold up. Riemann hypothesis, and why should I care?
Riemann hypothesis is like the holy grail for mathematicians studying primes. Tries to predict where they'll pop up in the number line. Sounds easy, but it's been unsolved for like over a century.
Wow.
Robbins' theorem is a possible way to prove it. It says, if a certain inequality involving our divisor function is true for all numbers above 50/40, boom, Riemann hypothesis is true.
So this little divisor function, which seemed so basic, could unlock one of the biggest mysteries in math. That's insane.
It really is. Mathematicians are running calculations on huge numbers, seeing if Robbins' theorem holds up. If even one number breaks the pattern, the Riemann hypothesis could fall apart. It's high stakes.
I need to sit down for a sec. Divisors, primes, Riemann hypothesis, it's all connected.
Exactly. Shows how interwoven math is. And it gets wilder when we talk asymptotic growth.
Asymptotic growth. Sounds kind of scary.
It just means what happens to a function as the numbers get really, really big. Like, imagine graphing the divisor function. As you go along, the values jump around, making a cool pattern. But mathematicians want to know the overall trend. Does it keep jumping randomly or settle into some predictable thing?
So it's like seeing the forest for the trees, looking past the jumps for the big picture.
Exactly. And some functions, like the sigma function, which adds up all the divisors, they grow in a way we call unruly.
Unruly, so not a straight line or smooth curve?
Nope. More like a vine, growing wildly, branching out everywhere. It still has rules, but they're way more complex.
We went from cake to unruly vines taking over the math universe. My brain needs a break. But before we wrap up, any last bits of divisor wisdom?
This reminds me of Euler's pentagonal number theorem. Euler, a famous mathematician, found this cool link between pentagonal numbers, the ones you arrange like a pentagon, and partitions. Like a secret passage between two different rooms in a mansion. Shows the surprise connections that pop up in math.
Euler and his pentagonal numbers, huh? It's wild how these connections just appear in math.
It really shows how elegant and interconnected everything is. You know, even something as simple as divisors can send you down these rabbit holes.
It's like each number has its own story. And we're just starting to peek at the first few chapters. But as we wrap up on divisors, any takeaways you hope listeners get?
I hope they've got a new appreciation for those aha moments you find even in the simplest math. We began with dividing a cake, and look where we ended up. Prime factorization, unruly functions, even the Riemann hypothesis.
What a ride. We've definitely shown divisors aren't boring.
Absolutely not. And this is just the beginning, really. There's so much more in number theory.
So any parting words for our listeners before we send them off on their own math adventures? Something to think about with their newfound divisor knowledge.
How about this? We saw the divisor function makes these cool patterns on the number line. But what happens is those numbers get huge, like astronomically huge. Do the patterns stay the same or change completely? Keeps mathematicians up at night.
It's like looking out at space. We've only seen a tiny bit. So to our listeners, if you're feeling up to it, check out the OEIS and Wikipedia links. Maybe you'll make the next big discovery with divisors.
Happy exploring, and always stay curious.
From cake to the mysteries of the universe, divisors are way more interesting than they seem. Until next time, keep those minds hungry for knowledge, because sometimes the deepest dives uncover the most unexpected treasures.